These analyses help provide government and business leaders with critical decision-making information. Today's 2020 Climate Assessment webinar will feature a short presentation followed by a media question and answer session. This webinar's audio and a copy of the presentation will also be streamed live by NASA at www.nasa.gov/NASA Live. Our first presenter is Russell Bose, Chief of the Analysis and Synthesis Branch at NOAA's National Centers for Environmental Information in Asheville, North Carolina. He will provide a summary of NOAA's 2020 global temperature and climate data. And our second presenter is Gavin Schmidt, Director of NASA's Goddard Institute for Space Studies in New York, New York, who will summarize NASA's average global temperature data for 2020. Gentlemen, the floor is yours.
Hey, thanks, Sean. And just to start off real quickly, I wanted to thank a couple of folks at NCEI, Ira Sanchez-Lugo and Karen Gleason, who take point on so many monitoring efforts, and Matt Minet and Byron Gleason, who take point on making sure the data are ready for folks like myself and Gavin to make use of. So this was definitely a team effort. So 2020, just to make sure we're all on the same page here, both NOAA and NASA use data, basically data. We're talking about sea surface temperature data from ships and buoys and floaters, and air temperatures from surface weather stations. So the highlights this year for NOAA, NOAA was ranked second in this record dating back to the late 19th century. The anomaly was 0.98 degrees C, which was 1.76 Fahrenheit above the 20th century baseline. Again, just slightly cooler than 2016. In other words, again, NOAA ranked number 2. Our calculations suggest that there's only about a 29% chance that 2020 was the warmest year on record. Gavin will give you the NASA highlights in a moment on that. Having said that, the ranks are a little bit like clickbait. They don't tell the whole story. What's more striking really is the last 6 and 7 years have been, they really stand out above the rest of the record. They hinted at, they really suggest what kind of rapid warming we're seeing here. Looking a little further back, each of the past 4 decades has been warmer than the decade that preceded it, and there's been a steady increase in temperature since the 1960s. If you go back even further, 2020 was 1.19 degrees Celsius or 2.14 Fahrenheit above the average for the late 19th century, which is a reasonable surrogate for pre-industrial conditions. So the planet's closing in on the 1.5 degrees Celsius of warming discussed in the Paris Agreement. It's certainly warmer now than at any time in the past 2,000 years at least, and probably much longer. And there's a pretty good chance that the rate of increase in the past 50 years is faster than any time in the past 2 millennia. And with that, I will hand it off to Gavin.
Thanks, Russ. Similar to the NOAA data, the NASA data shows 2016 and 2020 very close together, though in the NASA data, 2020 is slightly ahead. But the differences between those years in both cases are actually well within the margins of error that we have for the uncertainty in these annual numbers. And so effectively, it's really a statistical tie either way. This is the warmest decade in the historical record without any question whatsoever. And there's perhaps a hint of an acceleration happening, but it's unclear whether that is a persistent signal or whether that will be simply kind of decadal noise. Russ?
So I think it's fair to say that 2020, and this is a bit of an old story now, there was record warmth over most land areas. The land surface temperature in NOAA was the warmest on record at 1.59 degrees Celsius above the 20th century average. The big story this year was Siberia. It was the hot spot. Though it seems like every year there's a hot spot somewhere, and this year it was absolutely Siberia. Much of the winter there was exceptionally mild, warmer than average spring. In May, some places were 18 degrees Fahrenheit above the average. There was a town in Siberia whose name I can't pronounce that was reported a high temperature of 100.4 degrees Fahrenheit, If that gets verified by the World Meteorological Organization, it'll be the first time there's been a weather station in the Arctic that's had a temperature above 100 degrees Fahrenheit. Consistent with the warmth over Siberia, the average annual Northern Hemisphere snow cover extent for 2020 was the fourth smallest in the record that dates back to almost when I was born, the mid-60s. That comes from the Rutgers Snow Lab. A couple of other tidbits, it was warm, so ironically, the northern sea route along the northern coast of Russia finally froze shut in early November. It was open more than 100 days. And I thought I read somewhere that 2020 was the busiest shipping season ever for natural gas tankers in the Arctic. So an indication of impact that you don't always expect. Warmth of 2020 occurred in a year that started with an ENSO winding down, El Nino winding down, and a moderate La Nina starting up. And you can see that on the map. If you look in the eastern tropical Pacific, you see sort of an area of blue. And my understanding is that La Nina the global temperatures lag La Nina by 3 to 6 months. So that suggests that 2021 may struggle to keep up with 2020 just a little bit, but we'll see what happens next year. Gavin?
Yes, so obviously the raw temperature data that we use and that NASA uses are basically the same, but we stitch these things together slightly differently. And the methodology that NASA uses allows us to extrapolate further beyond the coastlines in the Arctic, and so we estimate that the Arctic as a whole was exceptionally warm, not just Siberia, though that is where the most dramatic record warming that we saw last year has occurred. Russ made a quip about there are always hotspots in these maps, and that's true. The amount of area in any one year that is now 3 sigma above the baseline, which is a standard definition for an extreme, is now close to 20% of the area on a year-by-year basis. And if the climate was static, that would be something down in the 1% level. We are seeing more and more heat waves, and it's very, very clear in these data sets. So the pattern that you see there is very similar to what NOAA shows, with some extension in the southern high latitudes and in the Arctic high latitudes. The only places that were anomalously cool are really the areas around the continent of Antarctica. There are some cool ocean spots, and you may just be able to see a hint of a cooling in the North Atlantic. And that's a pattern that we think is associated with a change in the overturning stream function in the North Atlantic. But I'd be happy to discuss that later on. Russ?
Thank you, Gavin. One thing I wanted to point out on Gavin's map, NASA deserves a lot of credit. They were early out of the gate to say we really need to get some estimates of what's going on over the poles, and I think that led a lot of us to change the way we do business. So wanted to highlight that. Okay, this is not a case of confuse and conquer. That's not the point of this particular map. It's something we put out in our regular reports, and I do want to highlight a couple of things. These are significant events of 2020. The red circles indicate basically the status of heat events, if you will. And what you see is that Europe and Asia were the warmest. This is the warmest year on record. 2020 was the warmest year on record for Europe and Asia. South America came in second warmest. Africa and Australia were fourth warmest. And North America brought up the rear at 10th warmest. Sea ice, well, Gavin will talk a little bit more about the Arctic sea ice in a second, but as you might suspect, it's not higher this year. Antarctica was near average, and we don't see a lot of changes going on in Antarctica right now in terms of ice, probably because there's a lot of upwelling in the Southern Ocean in around Antarctica, and that tends to suppress the rate of temperature change there. In terms of tropical cyclones, I think there were 103 named storms in 2020, which ties the record in 2018. But there were 45 hurricane and 21 major storms. Those are actually pretty run-of-the-mill values. The North Atlantic played an unusually large role in the tropical cyclone activity this year. It accounted for about 30% of the global energy and named storms. That's about twice normal. One other point that's not called out on this map, but it's Australia. I'd almost forgotten this, but late in 2019 and early in 2020, there were a lot of bushfires in Australia. It was a record-setting year, I believe. More than 40 million acres burned, a lot of homes. But it spawned some of these things called pyrocumulonimbus clouds, and which injected a lot of smoke into the stratosphere, and that kind of then spun around the Earth like it usually does. And there's probably, I've seen at least one paper that suggested that this might have had a bit of an impact on global temperature. Not huge, but it probably made things just a tad cooler earlier in the year. Gavin?
Thanks, Russ. And so talking of things that affect the temperature, Russ mentioned the El Nino, the kind of slight El Nino pattern that we started with, and the transition to the La Nina pattern that we have right now. We can quantify the impact of the ENSO state on the global mean temperatures. And what you find is that it's the El Nino in the spring at the beginning of the year, the winter and spring at the beginning of the year, that has the most important effect because of the lags in the system. And we can try and then remove that from the record and end up with an estimate of what would have happened without changes in El Nino. And what we find is that years like 2016 would have been cooler by about 0.1 degrees Celsius, and years that had La Ninas, such as 2011, would have been slightly warmer without the effects of ENSO. And so there's a slight accounting for that on the slide here. And so 2020 got a small boost from the state of ENSO at the beginning of this year, and then as you'll see in temperatures from December and in the mean, the net effect was slightly negative. But if you look at the long-term trends, once you correct for El Nino, you see that the long-term trends are slightly clearer. And you see the big impacts of things like volcanoes a little bit more clearly. But without El Nino in 2016, 2020 would have been by far the warmest year on record. Russ?
Okay, now for something just a little different. Ocean heat content. Just in the way of background, sunlight hits the Earth's surface, the world's oceans absorb some of this energy and store it as heat. It hits the surface, but eventually gets spread to deeper waters. Currents move it all over the world and to progressively greater depths. As we all know, water has a much higher heat capacity than air. It means that the oceans can absorb large amounts of energy with only a small increase in temperature. Total amount of energy stored in the oceans is called ocean heat content, and because the oceans can store so much heat, they haven't warmed as much as the atmosphere, even though they've absorbed something like 90% of the Earth's extra heat since the mid-1950s. So if it wasn't for the large heat storing capacity provided by the oceans, the atmosphere probably would have warmed even more. With that background in mind, in 2020, the heat content of the upper 2,000 meters of the ocean was 255 zettajoules. I'll get to that measurement review in a second. That's above the baseline that goes from the mid-1950s to the mid-2000s. That's about 1 zettajoule above last year. So basically, it's kind of a wash. The difference isn't a big deal. It's probably within uncertainty. The bigger picture is that, of course, that the ocean heat content has been steadily rising along with global temperature going back any number of decades. As far as zettajoules go, for those who like or need some sense of scale there, it's 10 to the 22nd power. Here's the creepy point of reference. I think I heard last year that the amount of ocean energy going into the ocean every second is roughly equivalent to the energy from five Hiroshima bombs. So there's a lot of energy that the oceans store up. Other factoid, of course, because water expands as it gets warmer, the increase in ocean heat content also increases. the volume of water, which drives the increase in sea level. Gavin?
Thanks. As we mentioned before, the changes in the Arctic are very dramatic. And when we look at the temperature changes in the Arctic is warming at roughly 3 times the rate at which the global mean is warming. You can see that in the inset. There's noise in the Arctic, so there's more ups and downs in a small regional area than there is in the global mean. But it seems pretty clear that Arctic amplification is a very, very serious and dramatic consequence of the warming that's ongoing. That has impacts not just on temperatures, of course, but on the ice that is such a major feature of the Arctic. And 2020 was the second lowest ice minimum, which occurs in September, only beaten by 2012, which was a very exceptional year. And as you can see, it's getting to be almost a 50% decline in September sea ice since the 1980s. And so this is leading to, as Russ mentioned, increased shipping routes, but also big changes in ecosystems, storm tracks, sea level, indirectly and directly, because this is warming not just the sea ice, but also the ice sheets. And Greenland, as most of you probably know, is losing about 250 gigatons of mass every year as a function of the warming climate that we're seeing. But the changes that you see are in all seasons. So even though the changes in March, which is the sea ice maximum, are not as dramatic, it's still very clear, and it's clear in every single month. Russ?
Okay, so it often comes up, how different are the analyses? We get different ranks in different years sometimes, but that's not really the message. The message that we really want to get across is that the analyses really track one another over time, despite differences in methodology and coverage. That's what this plot is basically depicting here. These are the global temperature time series with respect to a 1950 to 51 to 80 base period for about 5 of the major products. Made this plot before all of them had the final value for 2020, but it doesn't really change the story. They all show that there's been steady warming, certainly over the past half century, and the disagreements are really pretty minor, again, despite differences in the statistical methods that are used to, say, adjust for historical changes in observing practice or the spatial coverage through time. And I think that's all I'm going to say about that. We basically want to send you the message that we're telling you the same story about long-term change, even though we go about things in a slightly different way, which is a good thing, by the way. It's good that different groups do things different ways and come to the same conclusion. Gavin?
Yeah, I mean, let me just add on that slide before, the differences between 2016 and 2020 in every single one of these analyses is all within the margin of error for any individual year within those analyses. But it's Russ mentioned, kind of led with the idea that it's good that we produce the same results. But we need to remember that the products that use the weather station data and the ocean data, we're all basically using the same raw data, but we're stitching it together slightly differently. And so while a similar result based on that different stitching is a validation of the fact that you haven't done something terribly wrong with your method, it doesn't tell you that you've really captured what's going on in the world. It's good to have totally independent data. And so we do try and assess how well our surface temperature products match up with independent sources of information about surface temperatures. One of those methodologies, it comes from the reanalyses project. So a reanalysis is a weather forecast that's run with the model fixed, and it basically just produces weather forecasts for the last 50 years using all the information that we have, which varies over time. and then we analyze the temperatures and that. So the top two, the top graph is for trends from 1979 to 2020 from the ERA5 reanalysis and then the GIS temp product. So ERA5 doesn't use quite the same data. It uses a lot more satellite data. It uses radiosonde data. That doesn't go into the GIS temp product, which only uses the weather station and ocean buoy data. But you can see that there is a very high coherence between the trends that are seen in the reanalyses and in the GIS temp product, and in fact the trends are almost identical over this period. There are some there's some resolutional issues. The GIS temp smooths over a larger area than the reanalyses would, and so there's a lot more. There's more structure in the reanalysis, but the overall patterns and the overall trends are very, very similar. So that's gratifying. Now there is another instrument which is called the AIRS instrument, which is flying on the EOS Aqua satellite, which is a NASA satellite, and this produces an estimate of ground temperature. So ground temperature and surface air temperature are not quite the same thing, but the anomalies in ground temperature turn out to be very correlated, highly correlated to the anomalies in surface air temperature. And so you can see here for the period that this satellite has been in orbit, the trends, again, the patterns are very similar. Now there's more of an offset between the weather station data and this satellite product, and it depends a little bit on the version of the satellite product you have. And so there's a lesson here, I think, in structural uncertainty. So there are structural uncertainties in the weather station and ocean station products, but where there are problems or inhomogeneities, they don't generally affect the whole pattern, whereas structural problems with satellite retrievals often affect the whole retrieval, and so there's more cooling that's being seen in the Southern Ocean in the AIRS product than we're detecting from in situ SST measurements, but it may be that we don't have very many measurements in those particular areas. So it's possible that that might be right, and we might be missing that. But then there are other things like in the tropics where the satellites seem to be seeing something that doesn't seem to be reflected either in the reanalyses or in the surface temperature data. But overall, the warming is still very robust. The trends are very similar within their uncertainties, and the patterns of change are very clear. And so we can say quite confidently that the trends that we see in these weather station products and the ocean products are not being overly affected by non-climatic issues. Russ?
Well, that concludes our formal presentation for today. Gavin and I would like to thank you for spending some time with us this afternoon, and we'd be delighted to take any questions you have.
Yeah, thanks again, guys. And now that we're going to be taking questions from the participants, I want to remind the participants that to do that, you can go to the chat function on this webinar. And if possible, please indicate who you would like to answer the question. For that, we already have, guys, believe it or not, a bunch of questions lined up to ask you. So I'm going to start at the top here. And these have not been, most of these do not have any specific person that they're asking, so feel free to answer whoever wants to jump in. Russ or Gavin, can either of you speak as to why Earth's temperatures are going up?
Yes, I'll be happy to answer that. So that's a question of attribution. And so, as we know, many things have caused climate to change in the past, from asteroids, wobbles in the Earth's orbit, moving continents. But when we look at the 20th century, we can see very clearly what has been happening. We know that the continents have not moved very much. We know that the orbit has not changed very much. We know when there were volcanoes. We know what the sun was doing, and we know what we've been doing. And we know that we've been increasing the amount of greenhouse gases prodigiously, more than doubling the amount of methane, almost 50% increase in the amount of carbon dioxide, increases in CFCs, which did not exist before. And also adding pollutants to the atmosphere, sulfates, nitrates, and the like. When we do an attribution by driver of climate change over the 20th century, what we find is that the overwhelming cause of the warming that we've seen is the increase in greenhouse gases. And when you add in all of the things that humans have done, almost all the trends, in fact, all of the trends over this period are attributable to human activity.
Wonderful. All right, thanks, Gavin. We do have another question here, and it looks like they're asking either one of you again. Do NASA and NOAA use different satellites or different data sets to get their numbers?
I can take that one. I'm pretty sure that, well, NOAA doesn't really use satellite observations for most of its global surface temperature product. We do use it a little bit in the oceans to do some quality control and to help establish some relationships for interpolation, if you will. I don't know, I'll let Gavin speak to the extent that NASA uses satellite observations for its work.
Thanks, Russ. No, so the GIS temp data uses only in situ data observations, weather stations on land, ship measurements and buoy measurements in the ocean. That comes from ICOADS, which is the ocean data set, and from GHCN version 4, which is the land surface data set. The AIRS data is a satellite measurement, so we use that for kind of evaluation of what's going on, and the ERA5 reanalysis uses a very large amount of satellite data in that it ingests on a daily basis.
All right, thanks, guys. And this is kind of a follow-up question to that. Given the importance of the Arctic warming, are efforts being made to collect better data, such as with satellites, so that we can include that in these analyses?
So I can take a little bit of that. Certainly, satellites have some advantages in the Arctic. They're not impacted by things like ice. It's hard to get a boat through ice for the most part. So that's one of the reasons that reanalyses have an advantage in doing full global coverage, because they can take advantage of the satellite observations, which help fill in those areas. There are some other sources of data for the Arctic. There are some buoys that actually float through the ice, and that's a source of temperature data that we've taken a look at and hold some promise for the future. Gavin, do you want to share anything else on that front?
Yeah, so I mean, we often get asked, well, why don't we just make one product which just uses all the information that we have, and then that will be definitive. One of the things that we like to do is not just to have one thing that we don't know how correct it is. So having different slices of the same pie allows us to test how robust the results are. And so I think that there's benefit in maintaining independent analyses from satellites, from reanalyses, and from in situ measurements. And where they all line up, we can have confidence that that is really reflecting what's going on. And where they differ, then we can look into why that might be. But if we just kind of lumped everything together, it would be very difficult to say where we need to do more work.
All right, thanks, Gavin. We have another question. This one is a little on the long side, so bear with me as I try to read it. The NOAA, at least, ocean data set shows rather strong warmth during World War II years that does not really show over land, making it seem as if the ocean data may be biased or lost. When included in global data sets, it makes these years look quite warm, even though they may not really be the case over land. Are there plans to try to get these apparent biases out of the record, as it does lead some mistaken thinking about natural causes such as solar versus anthropogenic causes.
I'll take a first stab at that. In the world wars are a very difficult time for observations for obvious reasons. So that presents a special challenge for when we try to make corrections to the historical record, because one of the challenges with the historical record is that early on, sea surface temperatures were measured with basically picking up buckets of seawater and putting thermometers in them. And as time went on, measurements techniques changed, and you measured the sea surface temperature through ocean intakes, for example. So there's a lot of work that goes into making those two alike. And it's a little challenging to do that during particularly the Second World War. But the message I think I'd really want to leave you with here is that those corrections are extremely important. If you don't make those corrections to the ocean data, you actually warm up with a much larger rate of warming than you do with the corrected data.
Let me throw in a little bit there. So there were real warm events happening in the 1940s. There was an extended, a very large El Nino event that's extended from 1940 to 41 that is well documented with in situ measurements at the time. And so, you know, there was something that was happening there. And in the North Atlantic as well, there is clear evidence that there was a warm kind of multi-decadal anomaly associated with that. So I wouldn't just assume that because you see structure in the temperature data that necessarily means that there are still biases in the record. We have worked on multiple versions of the sea surface temperatures, trying to reduce those biases, and I think we've done like collective. I mean, not me personally, but collectively, the community has done a very good job at removing the more obvious biases. There may still be some, and so you know these products are always works in progress. You know, they're only they're estimates of what we think has happened. We don't think that they're going to change very much, and the last sets of variations, going from ERST version 3 to version 5, or the HAD SST version 3 to version 4. They make some improvements, demonstrably they're better products, but the impacts that it makes in the global mean are generally small.
Right, thank you, Gavin. We have another question here, and let me get back to where we were because we're getting a lot flowing at the same time. How does the current seasonal trend of 50% loss in Arctic sea ice compare to previous seasonal trends for ice loss?
I'm not really sure what previous seasonal trend that would be referring to. You could maybe try in the chat.
Okay, and we can, and we'll ask them to follow up in the chat, please. Also, I wanted to ask you guys, we have had some questions for specific states or regions in the U.S. for the 2020 findings. Are you guys prepared to speak of those?
I can touch on them a little bit.
Wonderful. Well, Russ, one of them specifically is Florida.
All right, so what I'm going to do is speak in slightly more broad strokes. For the 48 states was fifth warmest on record, and most of the country, and I'm looking at a map now that's in the backup slides. I don't know that it's worth doing that right now, but most of the country, except for a small area in the Central Plains like Oklahoma, Arkansas, and adjoining areas, most of the country was above normal, and that includes Florida. Florida was on average 2 to 3 degrees Fahrenheit above the average for the 20th century. I can't tell you off the top of my head exactly where that ranks, but I can tell you that we have at the National Centers for Environmental Information a very nice tool called Climate at a Glance. If you have time on your hands, you can literally go to Google and type Climate at a Glance, and it'll bring you to a tool where you can like get all of that stuff at your fingertips. If that's not convenient, feel free to contact me after the call, and I can help you get some of those numbers more precisely. I'm not going to try to do that while on the meeting here today, because something will inevitably go wrong and I'll report the wrong number. So.
I appreciate it, Russ. And by the way, yes, that climate at a glance is great. And I can also, too, connect you with some of our subject matter experts who, specifically have been looking at Florida and other states in the U.S. If you want to reach out to me privately, my contact information is in the media advisory that we sent for this webinar. So thank you for that question. Let's get to another one here. Gavin, this one is for you. Could you talk a little bit more about the not so warm area in the North Atlantic?
Yeah, so that area just south of Greenland has been trending cooler over the last 2 decades. And that's where we expect to see the biggest fingerprint from a change in the ocean overturning stream function. There's been a number of analyses that try and pin that down, and I saw an excellent presentation on this just yesterday from people at Columbia University's Lamont Doherty Earth Observatory, and their analysis seems to indicate that the dominant change in that region is driven by the change in that circulation. So why might that circulation be causing a cooling? Well, it would be weakening. Why would it be weakening? From models, we understand that it weakens because of warming of the surface. So that reduces the density, and so makes it harder for the overturning part to come down, but also because of changes in freshwater. And we have got an anomalous amount of freshwater coming from Greenland, and that may be playing a role. The changes that one kind of infers for the change in the overturning stream function are of a few, maybe 10% reduction, but it's something that's very much something that people are looking into, very much an open question as to exactly what's going on there. But yeah, when you see everywhere warming except for like one spot, you have to ask yourself why. And I think that probably is the reason why, and we haven't really fully worked out what that means yet.
All right, thank you. We have another one, and Chelsea, I hope I'm pronouncing your name right, Chelsea Goad from space.com. She said this is for either Gavin or Russ. People saw emissions temporarily declining as a result of initial lockdowns in response to the COVID-19 pandemic. It seems that such a temporary decrease in emissions would not have an effect on warming temperatures over time. How have you seen changing human behaviors with the pandemic affecting change projections?
Oh, how about Gavin can do the projections part? The carbon emissions for 2020 declined by about 7% globally, I think, but atmospheric carbon dioxide levels still rose a couple parts per million to roughly 414 or something like that. And for the record, present day global concentrations of carbon dioxide are levels not experienced in probably a couple million years. As far as the lockdowns associated with COVID, yeah, they led to a temporary reduction in pollutants like carbon dioxide, but the influence on climate was probably small because different pollutants have opposing effects. So like cars and airplanes, they generate nitrous oxides. Those are greenhouse gases. So if you reduce those, it could have had a small cooling effect, right? The flip side, things like steel and cement manufacturing, they crank out sulfur dioxide, which turns into aerosols, which reflect sunlight. And if you reduce those, then you might have had a slight warming effect. There's not a lot of peer-reviewed work in this space yet, but I think Gavin could probably give you a little more perspective on the precise importance of those two relative forces and how it might play out going forward.
Yeah, thanks, Russ. Let me just correct you a little bit. The biggest changes have been seen in nitrous oxides, which are not greenhouse gases, but they are reactive and they produce nitrate aerosols, which are a cooling effect, but they also affect ozone levels. So they cause ozone to go up slightly, so that would be a warming effect. In work that was published earlier this year, I think before the full extent of the lockdowns had really become apparent, the cooling effects from the changes in nitrates and sulfates, so the reduction in nitrates and sulfates, which would lead to a warming of the climate this year, were kind of slightly balanced by the increases in ozone, hold on. You get an increase in ozone and a reduction in nitrates, so that therefore, both of those are towards the warming effect. And so those short-lived changes in 2020 are going to be the dominant terms. As Russ mentioned, the changes in carbon dioxide, we still increased carbon dioxide by 2 parts per million last year. So the changes in emissions, those aren't going to have a direct effect on this year. But the changes in aerosols and short-lived pollutants may well do. And I think we'll see some more peer-reviewed literature on that. Our internal estimate, so take this with a bit of a pinch of salt, suggests that you would have seen perhaps an effect of about 0.05 degrees Celsius warming because of the lockdowns. But that's small and so not hugely significant. But if you cared a lot about hundreds of a degree C, perhaps in terms of the ranking, then the COVID lockdowns may have made a difference there.
All right, thanks. Another question here. Speaking of trends, does it still make sense to report climate statistics relative to a fixed climatology, or should we begin reporting conditions relative to baselines that account for warming?
So, okay. Two things I want to emphasize here. The first is that the base period doesn't really affect the long-term rate of warming. It's just a point of reference for saying how much things have changed. And there are different schools of thought on that. And within NOAA, we actually do a couple of different things. For the global numbers, we tend to report them with respect to the 20th century average, just because then you get a sense for how far things have really drifted through time. We have another product line that are called our climate normals, or US climate normals, and we do those with respect to the most recent 30-year period. We'll be putting out the next edition of it later this year that covers 1991 to 2020. And those are geared toward a different application, which needs to know what the most recent estimate of, say, temperature is in a place. So different base periods have different purposes.
So the NASA data is always reported with respect to the same baseline for precisely those reasons. When you're plotting anomalies with respect to the latest climate normal, then you are losing some sense of how things have changed over time. So, in terms of media presentations, it's something always to be thinking about. What is the normal period that you really want to show the delta from?
All right, thanks, Kevin. Russ, we have one here for you. Russ briefly mentioned the disruption of the thermohaline drivers for the Gulf Stream. Could you elaborate?
I didn't remember mentioning any.
No, that was me, and I think I covered that in the previous question, so we can just skip that one, I think. So,
okay, thank you. This one appears to be for either one of you. Was it unusual that no state in the contiguous U.S. had its warmest year, and what accounted for 2020 ending up as 5th warmest in the U.S.?
I don't think it's all that unusual to have a year that ranks highly, but then few places wind up being record warm. Certainly one of the things that we expect with warming that's imposed by changes in carbon dioxide and other greenhouse gases is the warming is going to be widespread. So you don't necessarily have to see a record in any particular place to get a particularly warm year. And I'm afraid I forgot the second half of that question. Can you repeat that, John?
Sure. It says, was it unusual that the state had its warmest year, and what accounted for 2020 being the 5th warmest year for the U.S.?
I'm not sure I have anything particular to add to the second part of that. It was just, that was the way it turned out. For the most part, it was warm in most of the United States. but I don't have any real attribution details I can pass along there.
Okay, thank you. All right, now here's a question for either one of you, and bear with me. While it was only one drifting surface station, to what extent were the Arctic temperature interpolations impacted by observations from the Mosaic field campaign?
So I'm pretty sure that the Mosaic data has not yet entered into the ICOADS database. It might have, in which case I will stand corrected, but my guess is that it won't have done yet. But the key with those kind of in situ field campaigns is not to track the temperature or thickness of the ice, but to really look at the processes that are being involved. Mosaic, if for people that didn't know, was the biggest effort so far that the community has ever put together to embed a ship, two ships, in fact, in the ice and have it drift with the ice over a full year. We've done this a little bit before. The Sheba project did something similar, but the Mosaic was a better and bigger project. The idea there is to really look at what controls the melt, what controls the snowfall, what controls the sea ice formation, what controls the mixing underneath the sea ice. And those are key observations that we use when I'm wearing my other hat of a climate model developer to put into our representations of what happens in the Arctic and the Antarctic so that we can do a better job of modeling the whole system. But in and of themselves, they're not large enough or permanent enough to affect really the long-term trends in temperatures or ocean temperatures.
All right, thank you. All right, another one. It says, of course, is not evenly distributed, but how does having North America having only its 10th warmest year make it harder to get a sense of urgency?
I don't know that we're here to convey a sense of urgency or non-urgency. We're here to just share numbers with the American public and beyond. That's sort of our mission here, is to get information into the hands of people who need to make decisions, informed decisions. So this year it just turned out that North America wasn't as warm as some other places in the world, and that happens, but I'll leave it at that.
Okay, thank you. Another question for either one of you. On temperatures over the Arctic Ocean, what is actually estimated? Is it the air temperature over the ice or ocean, or is it the actual surface temperature? And how is it the fact that the freezing point of ocean water is less than the freezing of surface of sea ice than it is in fresh water? That was a bit of a
I can read it and I'll answer. So what we're trying to estimate is the air temperature above the sea ice. So if we had a weather station sitting on the ice at the 2 meter level, that's what we're trying to estimate. And so that has a correlation with air temperatures on land, which is why we can do that extrapolation that we discussed earlier. The questioner is correct. The temperature at the bottom of the ice is roughly minus 1.8, depends a little bit on the salinity, and that doesn't change very much from year to year because as long as there's ice there, it will be that temperature. So that doesn't really get accounted for in our estimates of the atmospheric temperature, though in the ERSST product, they do some interpolation where they see ice, where they assume that the temperatures, the sea surface temperatures, are at the freezing point. And so we're discussing with them, or we were earlier this year, on how we could make that a little bit more physical. But again, these are very small differences compared to the massive changes we've seen.
Thank you. Just to remind participants, we have about a little less than 10 minutes left, and it looks like we only have a couple of questions left, so we may be doing well with our time here, guys. This one is for either one of you. can you speak to some, I'm sorry, let me repeat that. Can you speak to some of the public health impacts of continued warming?
Sure, I'd be happy to. So there are direct impacts. So heat waves are a direct consequence of the fact that the planet is warming. And when you have intense heat waves, there are physical consequences and public health issues that are associated with that. But then we've also got changes, indirect effects, changes to drought, which can lead to soil drying, which can lead to agricultural issues. We have issues of forests drying, which lead to wildfires, and then smoke. Smoke is a big consequence of fire, obviously, and that has a very poor public health impact. You know, the changes in sea level have a public health impact because of the increases in storm surge or the increases in clear day flooding, as they call it in Miami. All of those things are associated with the large scale warming. Increased intensity of rainfall is a consequence of warming, and that is happening, you know, pretty much everywhere where we can detect it, and that has implications for the flooding and public health and public infrastructure damage there too. I could go into changes in disease progression. There's a lot of diseases where there is an element of some vector in the disease that is sensitive to temperature, whether it's the life cycle of a parasite or a life cycle of an insect or a plant. All of those things are being affected by the changes in climate. So the net effect of those is quite hard to predict ahead of time.
All right, thank you, Gavin. Russ, this one is for you. It says, Russ, any idea when we could expect the new climate normals, the 1991 to 2020 stats? Thanks.
Sure. NCEI is tentatively planning to release those in the spring. Our best estimate right now is May. We're bringing in the final data for 2020 right now. We don't get it all exactly on December 31st. There are some lags in reporting for some locations, and then there's a production phase that one has to go through in terms of assembling it all, doing the bias corrections, generating the actual numbers, and then doing quality control on the final product to make sure that everything lines up and you don't have any, say, rainfall values, normals that for some reason are below zero, or, neighboring stations that have wildly different things. So we just like to dot our I's and cross our T's before we release it. So we're looking at, later in the spring, tentatively in May sometime. And the person who's taking point on that is a great guy named Mike Pilecki at NCEI.
Thanks, Russ. Again, this is for either one of you. Is there a known lag effect to things that are happening on the ground and things that we are measuring? That is just, if all human activity that affected, if all human activity affected any climate measurement, temperature, ocean heat content, ozone layer, et cetera, were to cease, how quickly would it show up in the measurements?
So that's actually quite a good question. For instance, if we were to cease things that produce carbon, we would start to see changes in the carbon concentration immediately. When we cease polluting activities that produce aerosols or smog, we see the changes very, very quickly, within a couple of weeks. But we don't see the change so much in the temperature because, as Russ mentioned earlier on, the ocean has a massive amount of heat capacity. And so even if we ceased all activities that affected climate tomorrow, we wouldn't actually see a decrease in temperatures for many, many decades. So it depends kind of what you're looking at. I mean, take the ozone hole. We started to curtail the use of CFCs in the late 80s, 90s, and we've seen changes in the concentration of CFCs and HCFCs. But the recovery, the ozone hole, is kind of imminent, but it hasn't really happened yet. that's like a 20-year lag before the changes that we made in emissions of ozone-depleting substances are really going to have a detectable effect on the ozone hole.
All right. Thank you, Gavin. And it looks like we have about 3 minutes left, and we have one more question. So hopefully we can get this in on time. This is for you, Gavin. It says, extrapolation of the 5-year running average of NASA data suggests the world might exceed 1.5 degrees C warming by the end of the decade. Do you think this is part of variability or a real increase in the rate of warming, making exceeding Paris aspirational goal rather imminent?
So like looking at 5-year trends, those are not robust to internal variability of the system. So you can't extrapolate those too far. But you can do a statistical analysis and ask, given the long-term trends, when is the first year that we are likely to see a 1.5 temperature in the global mean set, and using the baselines that we're using now, which is the late 19th century, it's likely that we will have 1 year or so of 1.5 degrees before around 2030. And then we won't stay above that temperature for maybe another 5 to 10 years after that. I personally don't think that there's much that's going to happen that will change that, barring massive volcano that might slow things down for a few years, which is unfortunate, but that's what's likely to happen, in my opinion.
All right, thanks, Gavin. And that's the end of the questions, and we're at the end of our time.
John, there's a Tom Henry that's had his hand up the entire time.
I apologize, I did not see that. Would you like to take that one?
Well, he has a hand up, but he has to put something in the chat, otherwise I can't hear him.
Thank you for catching that, Gavin. If you still are there and like to ask a question, please feel free to drop it in. We're about at the end of our time. But what I can do, if I don't see that, I don't see a question yet. Let me at least let people know how to reach out to me so I can reach out to you guys after this, and we can maybe respond to the questions that way. First of all, Gavin and Russ, thank you so much for everything. It was great. I want to thank all the participants as well. If you have any further questions that we did not get to, please feel free to reach out to me, and I will reach out to Gavin or Russ. My name is John Bateman, and you can reach me at this email address, and I'll spell it, nesdis.pa@noaa.gov. That's nesdis.pa@noaa.gov. And I will get back to you as soon as possible. And this concludes today's AMS Town Hall and Press Briefing. I want to thank everybody again, and have a good year.
Well, thank you very much.
Thank you.